Today in lecture, we talked about how your book and most books have these two equations in them. Your book calls this one the point slope form of a line, and this one is the 2-point form of a line or 2-point equation. And I said in class that we never need these and we could pretty much forget about them. So I want to prove that that's true here. But first, right, I want to just kind of show or just have you notice that these are really the same equation, right? Like if m is the slope, well, that's exactly what that thing is if you don't know the slope, but you know 2 points. What do I mean by that? Let's just take a look real quick. Let's say that we have some line. And it doesn't matter that I'm drawing it like this. The picture would be the same if it were way over here or something, but just in general, this is what this guy looks like. Okay, so that's a line. And we could say, all right, then what is the slope? Right, it's the rise of the run. The thing about a line is that its slope is always the same. The slope is never changing. We're never getting that the rise and the run are getting bigger or getting smaller. It's always the same everywhere on the line. So it doesn't matter what 2 points we take to calculate the slope. Right? We could take any 2 points. So let's do that. Let's say that we have some input value here. We're going to call it x1. We have some output value here, and we're going to call it y1, right? Because it's the output with that input. Similarly, if we have another point here, x2, then we have an output point here, y2. Then the rise over the run is just how much it increases, right? The increase in the height or the decrease. I could have drawn it as a downward facing line, and it's the idea is the same, but it's the change in the y direction divided by the change in the x direction. It's really, we're just talking about those two distances right there. And we could see, like, to find that distance, we just take that number minus that number, right? Like if this were a height of 1, that were a height of 5, we'd say, well, the difference from 5 down to 1 is 4, or in other words, 5 minus 1 is 4. But in symbols, since we don't know what these outputs are, we just say, well, that's y2 minus y1. That is that height right there. That's that distance. The run, similarly, we say, well, this could be, say, like 3, and that could be 5. We would say, well, the distance between those two is whatever that one is minus that one, right? It'd be 5 minus 3 would be a total of 2, but in symbols here, x2 minus x1. And so from all of this, we would have that the slope, which should be the same everywhere on this line, regardless of what 2 points we took, right? Anywhere on this line, it's going to give you m equals the rise over the run. So the height, which is y2 minus y1 over x2 minus x1, right there. So another way of thinking about this really ugly equation is it's kind of like saying, if you have 2 points, if you're given 2 points, you could calculate the slope just like that. And then instead of thinking about it like that, we could just really say, you're just using this equation right here. It's just that your slope is that guy, right? Okay, now let's say, but yeah, and what I'm trying to do now is I want to show that we don't need these guys right here. And so what I'm going to do is, if you remember in class, I said that the method that we use for doing this will be the same no matter. We'll cut that. So now what I want to do is use the same method that we did today in class. But we're going to do this in general, right? What we did in class is we had two distinct points. I think it was like 1, 2, and then 2, 6, right? So we had these two named points out in space. I said that all we need to do is just kind of go through and use our brains to find the answer, you know, to get through and to get the equation of the line that we're looking for. Well, let's do the same thing, but in general here. Right. What we're going to end up getting out of this is we're going to prove that the method that we're going to use from now on is exactly the same as this thing right here. There's no difference. Okay, so let's just go through the way that the way that we were saying to do this. So, okay, find the equation of, okay, so what do we want? We write down what we want first, right? My goal is to have a y of x, a function of x, equals mx plus b. That is the thing I'm looking for, okay? So now I know, well, hold up. I'm just looking for two numbers, basically. I need that number m, and I need that number b, and then I'll have the equation that I'm looking for. And so now, well, I'm thinking, if I draw this out, some things might become more clear to me. So I'm just going to draw it out. Again, notice, hey, I don't know where these points are. I could pretend that they're anywhere. And I'm going to say, okay, well, why don't we put this first point right here? And then, well, okay, then the input value is x1. The output value is y1. This second point, oh, I don't know. I'll put it right here. And we'll say that the input value is x2. The output value is y2. Okay. Now I'm going to say, okay, what can I do with that? Well, what do I need? Well, I need a slope and I need an intercept. Right now, I don't see how I'm going to get an intercept out of that, right? I don't see where this thing, because I just drew 2 points. I could have drawn them anywhere. They're not necessarily gonna, I don't know if this is gonna go through here, if it's gonna go through here. But one thing I do know, though, is that I can calculate the slope, right? I could find that rise over the run right here, because I have that information, right? I have y2 and y1, so I could say, well, then that height must be y2 minus y1. Maybe that looks familiar. And then that there must be x2 minus x1. Okay, so then this right here tells me that the slope of this line that's going to be passing through here, this line that I want, I know that m must equal the rise over the run. Okay, y2, y1 over x2, x1. Okay, so we got one bit of information. All right, so we're halfway there. We're halfway done with our problem. Now, what I'm going to do is say, well, why don't I just plug that guy in? Right? I mean, I have an expression for that number. So why don't I do that? Okay, y of x is equal to this stuff, y2 minus y1 over x2 minus x1. That times x plus b. You know, it could be really confusing, and I don't think we've talked about this before. Is like, we have to keep in mind that x and the output are kind of tied together, right? And there's not just one x that works. Let's understand the context, right? We're talking about a line. Lines, most of them go on forever in like a bunch of directions, right? They're going to go forever this way and that way. They're going to go forever that way and that way. They might go off like this, but the point here is that it's not just one or two x's and y values that work, right? There's infinitely many x and y values that work. And so we're kind of treating this guy as, well, he could be anything. I want to be able to plug in a 1 in there. I want to be able to plug in a 2, right? And so that's when we're looking at this equation right here, we understand that this is a variable. That's why I like to write it like that, because it means that's an input. And we could change it. We could plug in a bunch of different numbers in there, infinitely many, in fact. And we will get, for every one that we plug in, we'll get a different output value too. And so those things are linked together, right? And so when I'm looking at this thing here and thinking, how am I going to, what approach am I going to take to solve this? What I notice is that these guys are linked together and they're going to change. They're going to take on a bunch of different values. The only things that aren't ever going to change are M and B. And so then that becomes my focus. You know, and I think I've said that a couple of times now. Once I write that up, I'm thinking, okay, I need two numbers, M and B. And so those become my goals. And you might be thinking, well, wait, but we need more than one number. We need infinitely many numbers, right? It's like, yeah. But to describe this thing, that any line is entirely described by those two numbers right there. So whenever we have something that says find the equation of a line, we're thinking, okay, there's two numbers that I need, M and B. Now I'm at this point right here where I have almost everything I need. The only thing that's left is B. And I'm thinking, well, if I could get rid of this X and this Y right here, I'll have B all by itself, right? And then I'll be able to rearrange the equation and get an expression for B. And, you know, we're imagining that these are actual numbers, that I took like 5 minus 2 and got 3, and then like 4 minus, and then did something and I have an actual number there. Then the only thing that's left to determine is B. And if I could plug in two more numbers, then I'll have a number times a number equals a number. Could put all of those together and get B all by itself. In other words, solve for B, right? So let's do that. We have a relationship, right? We know that whenever I plug in an X1, I get out a Y1. In other words, we know that when X1 goes in, Y1 comes out. So let's go ahead and write that. We're going to say Y of X1 is equal to Y1, right? We're just saying plug it in, that pops out. On the other hand, we could say, well, this means that when I plug in an X1 right there, we get this. So this ugly thing here, X2 minus X1 times X1 plus B. So now I'm just going to forget that he's there right now and say, yeah, that means that Y1 equals that. And this is what I was saying, right? Like, now that's just a number, it's like 7. That's a number, it's like 2. That's a number, it's like 3. We multiply them together, and then we can get B by itself. Okay, in other words, I want B by itself. I'll subtract whatever number that is and get him over here. So explicitly, minus that value from this side. Y2 minus Y1 over X2 minus X1 times X1. Do the same thing over here. Minus Y1, X2 minus X1 times X1. These guys cancel out and leave me with B. Now what's left? Y1 minus that amount. What is that amount? Well, that's Y2 minus Y1 over X2 minus X1 times X1. Now, what was my goal? I needed two numbers. I needed M, which I have. I needed B, which I have. So now I'm going to take that and plug them into this original equation, and let's see what we get. I'm going to plug in M into there. I'm going to plug in B into here. So the thing I wanted, the equation of the line, is y equals mx plus b. We know that m equals that. So let's plug him in, and we'll rewrite this as y equals y2 minus y1 over x2 minus x1 x, right? And now I'm just plugging in numbers, right? So that m is that number right there. x, not using my brain, just plugging them in. B is equal to that quantity right there. So that's y1 minus the quantity y2 minus y1 over x2 minus x1 times x1, that entire number times x1. Okay, now let's rearrange this a little bit. I don't know, let's get all of our y's together. Okay, so subtracting y1 from both sides gives me on the left y minus y1 equals that ugly thing, x minus, again, that ugly thing, y2 minus y1 minus x1 times x1. What we have here is something that's maybe hard to see, but if, for instance, we had something like, oh, I don't know, if that m worked out to be 3, and we had 3x minus 3x1, what would we do to simplify that? Well, one thing we could do is pull out those 3's, right? We could say this is the same thing as pulling the 3 out front. And we could double check that that's the case, that that equals that. We just plug them back in and say, okay, the 3 goes and hits and becomes, yeah, 3x. Then it jumps over the negative and hits the x1. And yeah, those are the same thing. It's kind of hard to see when it's this ugly, but it's the same principle, right? That value right there, y2 minus y1 divided by x2 minus x1 is just some number. It might be 3, right? And so we could treat it like a number. We could pull it out. Let's see what we get. Okay, I'm going to bring the whole thing down a little bit and write y minus y1 is equal to, okay, so I'm going to pull that number out front. What's going to be left over is this x minus x1. That number that I pulled out front is y2 minus y1. And what do you know? It's exactly the same as that equation, right? Now, why they do that? I feel like what they do is they want to give you a general formula so that what you could do is, given any 2 points, you could just plug them in. And this does look slightly more simple than this right here. This is, if you notice, right? This is y equals m x plus, and look at that, that was b, right? That whole thing right here was b. It is y equals mx plus b, but then it's just kind of rearranged so that we have less plugging in to do. But again, like we said earlier today, it's like when you do this, you're losing the reasoning behind all of this, you know, and then this becomes just something that you learn, and for some reason you get it in your head like, well, this given 2 points, this is the equation you have to use. And it's like, this is just made up. This is the only thing that's real when we're talking about lines, right? That is our definition of a line. And everything else that comes from it is like, well, if you really don't want to use your brain and just memorize that, yeah, given 2 points, plug them into here, then yes, you will get the equation for a line, but I don't think the trade-off is worth it, right? First example, find the equation of the line passing through the points -1, 3 and 3, 5. Okay, let's do the plug and play method first. So we have, I already have it written out. Okay, so y minus, let's see, y1 is going to be the first, we'll call this point 1. So this is x1, y1, 1 is 3. Equals, okay, y2 minus y1. y2 is -5. y1 is 3, so -3. x2 is 3. x1 is -1. Uh-oh, minus -1. Don't want to mess that up. Okay. X minus x1, x1 is -1. -1. Right? Yes. Okay, now let's simplify. Y minus 3 equals -5 minus 3 is -8. 3 minus a negative plus a positive, so we get a 4. Okay. Y minus a negative is plus a positive, so we'll x plus 1. Okay. -8 divided by 4 is -2. So y minus 3 equals -2. X plus 1. Okay. Distribute the 2. -2x, -2. Okay. Plus 3 both sides. And we get y by itself, finally, 2x plus 1. And we're done. Okay, that's how we did it there. Now, let's do it this way. Find the equation of the line passing through 2 points. So I'm looking for y equals mx plus b, and I'm going to graph these guys. -1 is there, 3 is there. We have 3 and -5 is down here. I don't care what the measurements actually are. So let's find the rise. The rise goes from 3 down to 5. So that's 5 units there, 3 units there, a total of 8 units. And I could see that it's actually a fall, so it's -8. Okay. 3 units here. 1 unit there is a total of 4. And so the slope is -8 over 4 is -2. Now, y equals -2x plus b. I just plugged in m for m. Now I can take any point that I want, and it says when I plug in a -1, I get out of 3. So I'm going to plug in a -1 and get out a positive 3. Okay, so 3 equals +2 plus b. Subtracting 2 from both sides gives me 1. B equals 1. M equals -2. So y equals -2x plus 1. Much easier. and notice, like, I didn't bother with negatives, did I? I was just thinking in terms of lengths, right? This really messes me up, and you're inviting a mistake somewhere, right? When you have minus a negative, right? Or if you had a negative minus another negative, that's going to be, I hate that. I hate having to think about that. And 9 times out of 10, I'm going to do something wrong, right? So what I'd much rather do is just think about lengths here. It's like, okay, well, that total length from there to there is 3, from there to there is 5. The total length is 8. Is it going up or down? That's going down. So it's a -8. It's a fall of 8. What about from here to here? Yes, it's true that it's 3 minus -1. That's true. The formula is true, right? But I'd much rather think if I had a ruler, right, and I measured that long and I measured that long, put them together and we have that long. Now, if you have like fractions and stuff, right, like if this were instead of 3 is like 3/17 and -1/5, then you might want to recall and say, you know what, it might be easier to use, well, we're not going to use that. Don't look at that. We're going to say, well, we'll take this value minus that value. Or we'll take this value minus that value. But for the most part, it's pretty straightforward, especially when you could just see the lengths, right? Last example. We're going to find the equation of the line passing through the points -1, -2, and -5, 1. Let's use the formula method first. So y minus y1, we're going to call this 1. So that's y minus a -2.
okay, equals y2, which is that guy. So 1 minus y1 is -2. X2 is -5, minus x1 is -1. Okay. Now x minus x1 is a -1. Okay, y minus a negative is a plus a positive. Minus a negative is a plus a positive. And again, that's a +1. One more time, x plus 1 right there. Okay. Y plus 2. Now we get a 3 over, let's see, -5 and 1, that's -4. X plus 1. Okay. Y plus 2. I'm going to distribute this guy to get -3/4 x minus 3/4. Now I'm going to subtract 2 from both sides. Okay. -2, but I'm not going to write it as 2. I want a common denominator. So what divided by 4 gives me 2? I guess that's 8 right there. 8/4 is the same thing as -2. Okay, good. Now that gets rid of that guy, and we get -3/4 x. 8, 9, 10, 11, -11/4. Done. Okay. Now, the other method. Write down what we're looking for. Y equals mx plus b. That's my goal. Okay, now let's graph this thing. We got something might look like this. Okay, so we have a -1 and a -2. We have a -5 and a 1. Okay, so my line's going like this. I know it's a fall, so my slope's going to be negative. And we have 2 here and 1 here. That's a total of 3. And we have from 1 down to 5. That should be a total of 4. So my slope is the rise over the run, but the rise is actually a fall. I could tell. So -3/4. Okay, plug that in. And so we get y equals -3/4 x plus b. I could take either of those that I want to plug in. How about, that one looks easiest. So I'm going to say when I plug in the -1, I get out a -2. Yeah, -1's input, -2's output. Okay, so that is then a positive. Negative times a negative is a positive. 3/4 plus b -2. So we have -2 minus 3/4 equals b. But I'm going to rewrite -2 as something over 4. So that's actually 8/4 minus 3/4 equals b equals -11/4. That's b. Okay, what was my goal? To get that, and I have m and I have b. So y equals, going to replace the m with that number. I'm going to replace b with that number right there. Done. All right. So I love this method. And it's the exact same thing, right? Like we saw earlier in this video, right? They mean exactly the same thing. We actually ended up doing the same thing, right? Like look at that, right? We ended up doing all of the same calculations, but this is in context of something real, right? Or as real as math gets, right? But I could touch this. This is tangible to me, right? I have a feeling of what this is. Whereas this, I'm just trying to remember, well, negative minus a negative is a positive. And wait, which one was my 1 and my 2? And I'm getting them all backwards. And actually, you didn't see, I actually messed this up when I was doing it earlier because I just had a hard time keeping those straight, you know? Now that we've seen that this method makes more sense, right? It's more intuitive. It's easier to work with, really. We can forget all about this stuff forever. We never need to know it. or can we? What I'm going to suggest you do is go back to the beginning of the video and pause it once or I mean, you could just do this on your own, right? But I would say start off with this picture right here. Or better yet, start off with this question, but with x1, x2, I mean, x1, y1, x2, y2, and just go through this method to derive this the same way that I did at the beginning of the video, right? Do that so that you believe it yourself, that yes, it's true, right? Then once you know that, right, well, you'll probably never forget that. That's the thing about it, right? Once you derive something yourself, once you start from first principles, right? When I just say, if I were to just say x1, y1, x2, y2, now you go derive that formula, you'll probably remember it forever. And if you see it again, you'll go, oh yeah, I remember doing that. So I would suggest that you do that because you might see something like it again, right? Or at some point you might have a teacher who refers back to it. So you don't want to completely just jettison it from your brain altogether. But as far as actually working problems, you do not have to have this stuff memorized. And in fact, I think it's detrimental to do so. Because as you can see, when I was doing this, all you're doing is plugging in numbers and just messing with arithmetic. With this, you're actually using your brain, right? And you're keeping the bigger picture in context. It's like, yeah, I have a line and I'm trying to find its slope. And I want to know, given an input, there's an output. And now I have an equation for that line. You know, it's much, much better. So I think that's all for today.